Hello, my name is Pengfei Ji. This is my presentation on combustion dynamics in a Rijke tube. I'm in group C4. This is a 2610 spring 2020. First of all, introduction. We would like to discuss the importance and working principles of the Rijke tube as it could produce thrust without any moving parts such as compressor. We would like to discuss the periodic fluctuating properties and acoustic oscillation of Rijke tube. It has the property of in and out of phase oscillation. It has the ability to enhance the mixing of fuel and combustion quality due to increasing reaction rate and heat release. We also observe the interaction of heat release from fluctuating reaction rate, pressure feedback, and velocity fluctuation. We will also like to discuss the usage of piezoelectric transducer, photomultiplier, and rotometer. The piezoelectric transducer is used to measure the pressure readings from the tube at different locations, and we'll also use photomultiplier to measure the reaction rate and heat release, and we use the rotometer to measure the flow rate of propane fuel. The goal for students is to understand the periodic fluctuating properties and acoustic oscillation of a Rijke tube and have the exposure to the experimental results measurement equipments such as piezoelectric transducers, photomultipliers, and rotometer. Second, for data collection and experimental setup. For the experimental setup, we have three pressure transducers, each about 18 inches away from each other, equally spaced along the tube. And we have a quartz window installed to allow observation and photomultiplier sensing. And we're also implementing a marking adjacent to the quartz window for burner reaction position reference. We have adjustable height for the propane burner using a scissor lift. We have pressure release valve for resonance control and a thermocouple for measuring the temperature within the combustion chamber. The mechanism of a rotometer. First of all, the rotometer is used for measuring propane fuel flow rate. It utilizes buoyancy due to pressure differential and the weight of the float to reach equilibrium, at which the float will sustain at a specific location, and the height of the float correlates to specific flow rate. For the experimental setup, first of all, we calibrate the system without causing any resonance. This is done using figure 7 and 8 from lab manual, which is also presented at the last slide of this presentation. And after calibration, we set up all the inputs of data sensors, such as low, middle, and high pressure transducers and photomultiplier. Then we start our first step of measurement is measure the response at 0-inch mark with valve open, and then we measure the response at 0-inch mark with valve closed, and then at 2-inch mark with valve closed, and then measure the response as the height of the burner steadily increase until no pulsation. And then last but not least, we also find the location where pulse starts to generate again as we start from the top of the combustion chamber where the quartz window is located to going down, and eventually we observe the pulse start again at around minus 0.6 inches. For the data measurement, the Rijke tube has a total length of 72 inches. The distance between pressure transducers is 18 inches apart. For flame observation, at 0-inch valve open markings, we have high flame and there's no resonance pressure reading. But when the valve is closed, we see jumping flames, and also we have spotted resonance from the pressure reading. At the 2-inch mark, there's still resonance spotted, and we also have jumping flame. And during the pulsation cessation trial, there's jumping flame becomes gradually unstable, and we also observe superposition of weak resonance. For the burner location where pulsation cease is about 6 inches based on the marking from the bottom of the quartz window. So our first task for data reduction is to convert voltage signal of pressure readings to decibel. And this is based on the calibration results for the pressure transducer. We found the relationship between voltage output and pressure input is 96.8 millivolts of reading equals to 1 psi of pressure reading. And with the given VRMS in volts for each trial, we use the following formula for conversion, and which Based on the figure 8 in the lab manual, we found the constant to be 96.8, and we use that to get the PRMS reading. And then having the RMS pressure reading, we can calculate decibels with the given constant of the PRMS threshold is about 2.9 times the 10 to the negative 9 psi. With the RMS voltage provided in each data acquisition file, we are able to get the sound pressure level for each pressure transducer during each trial. As presented in the table below, we can see the sound pressure level is within the range of 130 to 150. Our second task is to estimate resonant frequency. Given an assumption of molecular weight of air, room temperature, and specific heat ratio 1.4, we have the formula below. With molecular weight of air is around 28.96 gram per mole, and the gamma is 1.4. The temperature of the room is assumed to be 300 Kelvin, and the length of the tube is given as 72 inches, which is around 1.8288 meter. And now we have the resonant frequency, which is around 94.9. For the relative phase for each sensors, the photomultiplier, and the three pressure transducers, we compare their associative phase with the associative phase of the second pressure transducer, which is located in the middle of the tube. And now, as the table presented below, we have all the relative phase of each sensors at each trial. For the results, we are presenting the frequencies and amplitude in decibel for the three pressure signals and the frequency and RMS of the P photomultiplier signals for each of the trial. As presented in the table below, we have all the data. And second, we would like to present the relative phase angles of the peak frequencies of the three pressure signals and the photomultiplier signal at the 0-inch mark burner location. And here, as shown below in the table, we have all the relative phase angles. For the subliminal questions, first, if we found a filter which has the specification 415 to 450 nanometers, this filter cannot be used for the experiment because the light mostly emitted with the combustion of propane is in the wavelength of 306 to 311 nanometer. Using a 415 to 450 nanometer filter will block signals from the sensors, and we're not going to be able to observe any pressure readings from the experiment. And after we made this change, someone comes along who wants to refit the Rijke tube with a burner designed for hydrogen as fuel. The experiment will not work because hydrogen combustion mostly release flame of wavelength 308 nanometer. The sensor we replaced with the 415 to 450 nanometer will not be able to detect the reaction rate, since there will be no pressure reading, since all the signals will be filtered out with this fitting. And now, if we want to design a Rijke tube that is tunable, where the frequency is continuously variable over a small range, we will build a portion of the tube that is retractable. This way, the length of the tube will be variable for a small range, so the resonant frequency will be able to vary for limited range according to the resonant frequency formula, which specify it is speed of sound divided by 2 times the length of the tube. In conclusion, from this experiment, we learned the acoustic interactions within a Rijke tube and how it could enhance or diminish combustion quality if the pressure fluctuation and velocity fluctuation is in phase. It will cause an enhanced combustion, but vice versa, it will diminish the combustion quality if they're not in phase. But with this much benefit from resonance, we also see limitations because if we try to apply resonance combustion to current gas turbine engines or rockets, then it could have some serious serious damages because all the moving parts will not be able to withstand as the chambers start making resonance and constantly expanding and contracting in a significant um, margin. For error detection discussion, the amplitude of the sound pressure level is higher than expected with the provided voltage RMS values. And based on um, the whole, so after the whole experiment, I believe it might be due to precisions of the measuring device. There also it could come from vibration due to the combustion, since earlier we learned that the vibration of the combustion could very much influence the pressure reading, since all the pressure sensors are very sensitive to any vibration comes along from the tube. And we also could acquire better sensors for the measurements, and this way we could help to reduce the margin of error and get a more close reading to the actual performance of the Rijke tube. And here are the supplemental graphs for the calibration data we've been using for this experiment. Thank you very much.